Hi, in this video, we want to take a look at hypothesis testing to see if a regression model is informative. All right, so we're not looking at individual slopes. We're looking at the hypothesis that one or more slopes from a multiple linear regression model is non-zero. Right, and so of course this is going to be the f-test in normally distributed standard regression. Okay, so some assumptions. Remember that we have that y is equal to x times beta plus epsilon. The only randomness is in the epsilon term. X is considered a known constant, and beta is an unknown constant vector. The variance of the epsilons given x is constant for all I. So this is saying that the predictor variable values have no influence on the random aspect. And we're going to say that y is normally distributed with expected value x times beta, and then covariance matrix of sigma squared times I. Now, we're also going to make the assumption that x is n by k plus 1. K plus 1 is less than n, so we have more observations than we have predictors. And when I say predictors, that includes the intercept on this one. And we're going to say that x is full rank. Okay, and something that is just absolutely under the hood, assumed, implied throughout everything when we talk about the theory of linear regression is that x is a known constant matrix. All right, so if we think back to regular multiple linear regression, we have our beta vector. Well, that's beta sub 0, the y-intercept, and then there is the beta 1 vector. So this is a vector, and this is the vector of slopes. All right, so how we're going to proceed is that we're going to make the assumption that all of the x columns, that all of our predictor variables besides the constant, are centered at 0. So they have mean 0. This way, things are a little bit easier. We get things like out of the way. Why can we do this? Well, remember that if I figure out the slope given some predictor variables, and I figure out the slope after centering the predictor variables at 0, so I subtract off the column means, I get the same slope. So we can use whichever version is easiest for us. All right, so our test for overall regression, our null hypothesis is that our slope vector is the 0 vector. So this is a vector. And our alternative is that the slope vector is not 0. That means that one or more slopes is not 0. Now, you'll notice in this hypothesis test, this doesn't tell me which of the individual predictor variables are useful. It just says at least one is useful. All right, and we're going to go ahead and work with the centered version of x. So x sub c, and I'm just going to say x from here on out for x sub c, otherwise it's going to get crazy. This is equal to our predictor matrix times I minus 1 over n times the J matrix. And here, as we proceed, since we're dealing with centered vectors, if I center the constant vector of all ones, it has mean 1, that means that it's just going to be 0. So it's going to be meaningless. So we'll go ahead and just work with the predictor variables that do not correspond to the intercept for this. All right, so our model is that y is equal to the constant 1 vector adjacent to the centered predictor matrix times modified y-intercept, then the same slope vector as before plus epsilon, and that's a plus sign right there. Okay, so remember that we have sum of squares total, we have sum of squares error, and sum of squares regression. Remember that sum of squares total is equal to sum of squares error plus sum of squares regression. Okay, so pretty much standard. And sum of squares total is a deviation between y and y bar. Sum of squares error is the deviation between the model and the observations. And sum of squares regression is a deviation between the mean and the modeled values. All right, well, there's a nice formula that we're going to need to use, and this is from chapter 7 in the book. Sum of squares error can be rewritten as sum of squares total minus our estimated beta hat transpose x transpose y, and sum of squares regression can be written as our estimated slope vector transpose x than our slope vector. Okay, and sum of squares total can be rewritten as y transpose I minus 1 over nj times y. All right, so why do we care about this? This is a quadratic form. Once I have a quadratic form, I know that I have theorems to be able to tell me what's going on with this thing. So this is good. So sum of squares total is equal to sum of squares regression plus sum of squares error. Okay. So I'm going to go ahead and replace sum of squares total with this formula. I replace sum of squares regression with this formula. And I replace sum of squares error with this formula here. But I recognize that that's sum of squares total, right? So I put sum of squares total right there. Okay, so now let's go ahead and replace our estimated slopes with the corresponding formulas. All right, so I replace this beta hat with the estimated value. I replace this beta hat with the estimating formula. This one stays the same. And I replace this beta hat with the formula. Okay, well, when I look at this, I see that I have this and its inverse is in there. All right, well, then I'm just going to get rid of it, because if something's next to its inverse, it's an identity matrix, get rid of it, it's gone. All right, this part stays the same, and this part stays the same. So let's keep on going. All right, now what I'm going to do, I look at this and I see that I've got x transpose over here, and in the middle I have x transpose x inverse. Over here I see that I've got x transpose on this side, and then I have exactly the same thing in the middle, x transpose x inverse. All right, so what we're going to do, we're going to go ahead and say that x times inverse x transpose x transpose, this matrix, we're going to call it the hat matrix. We're going to call it H. All right, well, when I do that, this part becomes H. Boom, it's right there. This part becomes H. Okay, so, and then, but wait, there's more. I see y transpose, I see y transpose, I see y, I see y. I go ahead and I factor, I've got identity, 1 over nj, and I've got H. So boom, I've got that. All right, so now we have another formula for our sum of squares total. Now, there's more direct ways to go about this, because you'll notice that if I just, factored the h's would just cancel out and I'd get exactly the left-hand side. But this shows a stronger relationship between sum of squares error and sum of squares regression. But if I just wanted this formula, I could do it a lot more directly than even invoking sum of squares regression, sum of squares error, but whatever. Do it however you want to do. It's all good. All right, so here's a theorem for us. If we're working with centered x without constants, and H is the matrix as we just defined, so x times inverse x transpose x transpose, and x is full rank, has rank k. Remember, I don't have the constant vector in there, so it has k columns. Then we get 4 things automatically happen. First and foremost, H times I minus 1 over nj is equal to H. Second, H is idempotent and it's of rank k. I minus 1 over nj minus c is idempotent also. Its rank is n minus k minus 1. And then H times I minus 1 over nj minus H is equal to the 0 matrix. So realize that this is the 0 matrix. Okay, so how do we prove this? All right, let's do number 1. First and foremost, remember that our X matrix is centered at 0. So all of the sample means are equal to 0 for all columns. All right, well, if the mean is equal to 0, then that means the numerator has to be equal to 0, means the sum is equal to 0. The sum is equal to 0 means that if I take a column and I add them all up, I get 0. Well, another way to represent that is to take the transpose, multiply by I. Okay, so what happens here is I have H, and then I have I minus 1 over nj. Remember that this is a bunch of vectors of constant ones. All right, so when I distribute, I get H, then I get 1 over n hj. Okay, well, these are all ones. When I multiply through, boom, things are canceling out easy peasy lemon squeezy, because when I rewrite H in terms of the formula with X's, I see that I have X transpose J. That means that this is a whole bunch of zeros. That means that this vector is a zero vector when I take these two together. Well, anything times zero is zero. So when I take this and multiply all that, I don't even care about all this junk over here. I know it's going to cancel out. Boom, it's gone. And so I get H minus 0, and that's just H. All right, now let's look at number 2. All right, so H is idempotent. Idempotent means that if I multiply it by itself, I get the original matrix back. This is an interesting property of matrices. Only if I'm talking about numbers, and the only idempotent numbers are 0 and 1. If I multiply them by themselves, I get the same number back. 0 and 1 are the only ones that do that. For matrices, it's way more interesting. There's a lot more to work with for idempotent. Okay, so H squared is just going to be H times H. So I just literally just write out the formula. All right, well, I notice I've got X transpose X, and then I have the inverse of X transpose X. Well, those cancel out, right? They become I. Boom. Well, then I notice I've got X, the inverse of X transpose X, and then X transpose. Hey, that's the H matrix. Boom. We got this. Now, why is it that we can say it is rank K? Well, remember, X is rank K in the first place. So so when I multiply by the inverse here, multiply by the inverse, and here, so this is non-singular because it has an inverse. It's non-singular, so it has an inverse. So the rank does not reduce off of this. So really, in terms of rank, we're interested in X and X transpose. Well, they're full rank. It works out exactly the way we want it. All right, now let's show that I minus 1 over nj minus h is idempotent. Remember, idempotent means if I multiply by itself, I get the original matrix back. Okay, so I have this. I go ahead, I expand this out. It's a lot of terms, but everything's there. Now, what I'm going to go do, I'm going to go through, and I'm just going to clean up some stuff. Well, remember that we worked out that h times a constant vector is equal to 0. So this term becomes 0. And then this term becomes 0 by the same argument because of like the transpose aspect. Now, we've already established that H is idempotent, so this is just H. So we've got a lot of stuff that's canceled out. What's left? Or we have HC. We have HC. And so this, J squared is the N constant matrix, and then I'm dividing by 1 over n. So I get 1 over n j after I factor out the n. And then I get 1 over nj. So we're going to have some cancellation going on here. Then I get 1 over, all right, so here's the negative 1 over nj. Negative 1 over nj becomes this part here. This becomes this part. And I've got 2 h's to go there. And then I've got the identity. All right, well, these and this cancels to be 1. And this negative 2h cancels with the positive h. You get negative h. Boom, we've got it. All right, so next, if I multiply these two idempotent matrix, h times 1 minus 1 over nj minus h, all this junk right here, I get 0. Okay, so what do? We just expand out h minus 1 over n hj minus h squared. Well, h squared is h because it's idempotent. Boom, we got that. Then we know that h times a constant vector is 0. Boom, we get that. And then that just stays the same. Well, I have h minus h, which is 0. Okay, looking good. All right, now the rank basically works out the same way, just understanding how this ends up, just thinking about the linear mapping to the zero matrix. All right, so now if y is multivariate normal, expected value x beta, and then covariance sigma squared times I, then the sum of squares regression divided by sigma squared, which is the same as estimated slope transpose x, estimated slope divided by sigma squared. Then this is going to be distributed chi-squared with k degrees of freedom, and then we'll have a non-centrality parameter here. Looks very similar, right? Not quite the same though. And then our sum of squares error will divided by sigma squared will be chi-squared distributed with n minus k minus 1 degrees of freedom. All right, so how do we prove this? Okay, so we need to recall theorem that if y is normally distributed, multivariate, mu and sigma squared I as the covariance, then y transpose ay over sigma squared is chi-squared distributed, r degrees of freedom, and this non-centrality parameter, if and only if A is idempotent and rank of A is equal to R. Okay, so we've got a lot to work with right now because we've been working with idempotent matrices up, down, left, and right so far. So first thing I'm going to do, I'm going to say that my estimated slope is the standard formula that we know and love. All right, so sum of squares regression, I'm going to rewrite sum of squares regression here. Is my sum of squares regression formula, at least the numerator. I'm going to rewrite that using the slope estimate formula. I get all this junk right here. Now I notice I have x transpose x, and then its inverse. That cancels out. Okay, that cancels out because it becomes the identity matrix. So now I'm left with this. Well, I go, hey, that's the hat matrix. I put it in the middle. Now I remember H is idempotent of rank K. It's idempotent of rank K means I can automatically use that theorem that we just referred to a moment ago. All right, so that means that I know that y transpose H y sigma squared is going to be chi-squared degrees of freedom, and the rank is the degrees of freedom, and then this term right here is my non-centrality parameter. All right, so I go ahead and just say, I know it's chi-squared. I know it's k degrees of freedom. Now here, I have the I have mu transpose times the hat matrix times mu, and then divided by 2 sigma squared. Well, I rewrite this in terms of x's and betas, and I'll get exactly what I want. Because remember, mu is equal to x times beta. Boom. All right, so if we think for a moment, x times beta hat is equal to this formula. Well, that's the same as the hat matrix times y. If I replace this part with the hat matrix, all right, so if I think about my residuals, the difference between observation and modeled values, well, that's going to be observation minus modeled values. Well, modeled values is x times estimated slope. Okay, well, this is the same as hat times y. So I change this to y minus hat times y. I factor out the y. All right, so now I know that my residuals is equal to 1 minus h times y. Okay, so if I want my sum of squares error, what I do is I just multiply this vector by its transpose. So I do that. Now I remember that this is going to be symmetric because of how it's built up using the transpose of x and regular old x. And so this is a symmetric matrix, so I can get rid of the transpose because it's symmetric. And then I remember 1 minus h is idempotent, so then I get 1 minus h in the middle. All right, so I have y transpose, idempotent matrix, y. So then, boom, I just go through and apply the theorem. All right, so I know that sum of squares error divided by sigma squared is going to be chi-squared degrees of freedom with n minus k minus 1. And then I have a non-centrality parameter. At this point, I need to show that the non-centrality parameter is equal to 0. How do I do that? Well, I just go ahead and replace mu with x times beta. Once I do that, and I replace h with x's, and it basically just, this junk as I distribute, it all comes down to 0 in the middle. Boom, we got it. So once the centrality parameter is equal to 0, I know it's chi-squared with n minus k degrees of freedom. All right, so if y is multivariate normal with x beta expected value, sigma squared times I covariance, then sum of squares regression and sum of squares error are independent. Okay, how do we prove this? All right, remember that if A and B are symmetric matrices that are constants and we're dealing with multivariate normal on Y, then Y transpose A and Y transpose B are independent if and only if A times sigma times B is equal to 0. Okay, so sum of squares regression, I just write this in terms of the hat matrix, and I write sum of squares error in terms of the hat matrix again. Okay, well, I look at this and I notice that I'm going to just go through and apply this formula. A is equal to the hat matrix. Sigma is little sigma squared times I, and then B is 1 minus H. All right, so I'm just going to go write that down. So this A sigma beta corresponds to all this junk right there. All right, that's a scalar. That means I factor out the sigma squared. I'm multiplying by I. That does nothing. So I know this is sigma squared H times 1 minus H. All right, well, when I distribute, I have H minus H squared, but H is idempotent, right? So that's just H. H minus H is your hero, 0. All right, so what does this do for us? We know that A times sigma times B is equal to 0. And we're dealing with multivariate normal. Therefore, we know that Y transpose AY and Y transpose BY are independent of each other. Okay, well, that tells me that Y transpose HY is independent of Y transpose I minus HY. Well, this is sum of squares regression. This is sum of squares error. Boom, we got it. So this is nice. This is nice. So remember, normally when if I'm dealing with regular old random variables, you know, covariance 0 is a big deal. But since we're dealing with normal, we actually get a lot more for this. We actually get full-blown independence. Nice. All right, now this next one, if you just review the derivation of the F distribution, this just immediately falls through. It's beautiful, it's nice, it's easy peasy lemon squeezy. Basically, if I just take I'm just applying the F distribution from this particular manifestations of the chi-square distribution, and we got it. All right, so if Y is multivariate normal, expected value X beta, covariance of sigma squared times I, and we say that F is sum of squares regression divided by K sigma squared, sum of squares error divided by N minus K minus 1 sigma squared, which I can rewrite as sum of squares regression divided by K, sum of squares error divided by N minus K minus 1. Then this F is F distributed with K degrees of freedom, N minus K minus 1 as the second degree of freedom, non-centrality parameter of lambda minus 1. Where lambda sub 1 is just this part right there, which should be familiar to us by now. Okay, so one thing that's important about this, you'll notice that my F statistic, like in the derivation, I've got sigma squared, but when I actually get the value, the sigma squares have canceled out. So I actually don't need sigma squared to be able to run this hypothesis test. This is important for us. All right, that's all I've got for you. Take care and goodbye.